tone FM for arbitrary value of beta, right? So we got this equation, yeah. So this particular equation, and then we analyze it that it has got so many side frequencies, um, and when beta is small, we showed that it is equivalent to narrowband FM. It has got only two side frequencies, FC plus or minus FM, and then we also did this power. The total power in the FM wave is AC square by 2, Jn square of beta, and Jn square of beta when summed from n is equal to minus infinity to plus infinity is equal to 1, right? And more importantly, we said the total power in an FM signal is constant. So the carrier signal, the 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 carrier power changes. If there is no modulation, entire power in the FM signal is due to the carrier, and if there is a modulation, the carrier power gets reduced, and then modulation power will get increased. Then what we did was we wanted, so that was all for single frequency, in the sense m of t, the baseband signal when it contains a single sinusoid, right? Am cos 2 pi fmt. But what happens, we just wanted to see what happens when there are multiple frequencies in the m of t. So that's why here what we were trying to do in the last class, at the end of last class, is m of t consists of two frequency components, right? And we said that it has got two frequency components, f1 and f2. And it f1 has got amplitude a1, f2 has got amplitude a2, and then naturally it should lead to two modulation indices. One is beta 1 corresponding to frequency f1, so delta f1 by f1, that is equivalent to kf into a1 by f1. Kf is the frequency sensitivity of the modulator, like, right? So it determines per 1 volt how much the frequency will be deviated. It determines the frequency deviation. So in beta is equal to delta f by f. Delta f is the frequency deviation. F. So our signal will be v of t is AC cos 2 pi fct plus beta 1 sin 2 pi f1t. So this corresponds to the first modulating frequency, one of the components of the m of t, and this corresponds to the second component of m of t, right? So these two. Now what we want to do is we want to analyze this signal, like what are the side frequencies. See, whenever we say we want to analyze the FM signal, we want to see its spectrum, we want to see its bandwidth, in the sense how much in the frequency domain the frequency is occupied till what extent, what are the frequencies present in the frequency domain. So in the time domain, we know that if there is only one component, then it would be this, but when there are two components, so this is the unmodulated carrier frequency, and this frequency gets varied to these two are the frequency variations due to the modulating frequency. Now we will see its frequency domain representation. We don't derive it, so you need not worry, like it's not a derivation. We just make use of the previous derivation and then directly write the equation and then analyze and then see, make some observations on that equation, right? So before doing that, as I ran out of pages in this tablet, digital tablet, so I have to delete some of the pages here. So please bear with me. So I'll maybe, yeah, I'll write this again, like, quickly. So let me delete some of the pages here. Yeah, so here page. Yeah. So okay. So I'll start from this equation again. So I'll wait. Yeah. So let me delete this as well. Okay, and then yeah. So I'll start from here. So what we are trying to do is multi-tone FM. So as I said, we are considering two frequencies, F1 and F2, and that gives by F1. So delta F1 is KF into A1 by F1, and the second modulation index beta 2 is delta F2 by F2, right? So this gives rise to KF A2 by F2, and the time domain equation is AC cos AC cos 2 pi FCT plus beta 1 sin 2 pi F1T plus beta 2 sin 2 pi F2T. Yeah, just a minute. Yeah. So this is the multi-tone FM, right? So if you do the analysis of this FM, means that means if you do the complex Fourier expansion of this signal. See, how did we do single tone FM analysis for arbitrary value of beta? So we had some equation like this, right? We had only beta 1 sine 2 pi f1, and then we wrote it as e power j 2 pi fct into e power j beta 1 sine 2 pi f1t, and then we did the complex Fourier series expansion of e power j beta 1 sine 2 pi f1t. So if you do in the similar manner, okay, by following the procedure, procedure similar to the single tone FM, we can show that V of t is AC. Here m is equal to minus infinity to plus infinity, and then n is equal to minus infinity to plus infinity. Jm of beta 1 into Jn of beta 2 2 pi fct plus, yeah, just a minute. I had a, did I, yeah, so mf1t plus nf22. We have two frequencies, f1. So corresponding to that, it should be Jm beta 1, and we have another frequency f2. Corresponding to that, there should be Jn beta 2, right? So here we have two indices, m and n, right? So and its frequency, and if we take Fourier transform of this, by taking Fourier transform, what we get is V of f. V of f is AC. Okay, so there should be AC by 2, because this cos we will write it as e power j theta plus e power minus j theta by 2, right? So that by 2 will come here. M is equal to minus infinity to plus infinity. Uh, then n is equal to minus infinity to plus infinity. Jm of beta 1, Jn of beta 2 multiplied by delta of f minus fc minus mf1 minus nf2 plus delta of f plus f1 plus nf2, right? We get this. See, this equation is also similar to the singleton equation, right? So except that there is f2 here. So in the singleton equation, it is delta f minus fc minus mf1, that's it. But here, as there is a second frequency, there is an f2. Similarly here, because of the second frequency, there is an f2. Now based on this, let us make some observations, right? So what are the observations? So one observation is, we have a carrier component here also. See, here m goes from minus infinity to plus infinity. That means m also takes value of 0, and n goes from minus infinity to plus infinity. So n also takes value of 0. So when m is equal to 0, n is equal to 0, it becomes delta of f minus fc and delta of f plus fc here. So that means that is the carrier component, right? So the carrier component has got amplitude j naught of beta 1, j naught of beta 2, because m becomes 0 and n becomes 0 when we consider only the carrier frequency, right? Okay, so let's write that first observation. So what are the observations? So what are the observations? There is a carrier component. A carrier component at frequency fc, obviously, with amplitude, and the carrier component amplitude is determined by j naught of beta 1 and J naught of beta 2. Right? So you understand this, right? So if you go back to the frequency, see here, if I put m equal to 0 and n equal to 0, I get J naught of beta 1 and J naught of beta 2 into delta of f minus fc, right, plus delta of f plus fc. So that meaning the component and its amplitude is given by J naught of beta 1 into J naught of beta 2, right? So that's what we have written. Understood? So next go back to the second observation. Now carrier component is over. So think about the side frequencies. Corresponding to F1 at Fc plus or minus mf1 for m is equal to 1, 2, 3 and so on up to infinity, right? And their amplitudes are having amplitudes Jm of beta 1 and J naught of beta 2. Yeah. So first make a note of it, then we'll observe whether this is true or not. Right? So what I'm saying is that there are side frequencies corresponding to Fc plus or minus mf1. So m varies from 1 to 3 up to infinity. So Fc minus f1, Fc plus f1, Fc minus 2f1, Fc plus 2f1, Fc plus 3f1, Fc minus 3f, and so on. And each of such side frequency magnitude is determined by Jm of beta 1, but this is J into multiplied by J naught of beta 2, right? So note down this and then we'll go back just once to see that. Okay, so let me, okay, so this is the frequency component for corresponding to carrier frequency. So let me erase this. So what do we have now? I'm talking about, right? So now if you put n is equal to 0, if you put n is equal to 0, this will be J naught of beta 2 and we have m. So and this n I have made it equal to 0, but I'm varying m from minus infinity to plus infinity. Is beta 1, Jm of beta 1 into J naught of beta 2. And then here what will I have? Delta of f minus fc minus mf1 minus 0, because I have made n equal to 0, right? Plus delta of f plus fc plus mf1 plus 0. That means I'm having frequencies at fc minus f1 and fc plus f1, right? Fc minus f1 and fc plus f1, right? So that's what I have written in the next page. We have side frequencies corresponding to Fc plus or minus mf1, where m varies from minus infinity, where m varies from 1 to infinity. Because I have put here plus or minus, that means m varies from 1 to infinity. If I put it like this, Fc minus mf1 and Fc plus mf1, then m varies from minus infinity to plus infinity, right? So that's what That's what we have written. Just by copying the second point. What is that point? So here we have considered F1. Now you consider F2. Right? Consider F2. Side frequencies corresponding to F2 at Fc plus or minus NF2, where n is equal to 1, 2, 3 and so on, having amplitudes, and each frequency amplitude is determined by J naught of beta 1 into. See, here I have to put m equal to 0 to have side frequencies corresponding to only F2, and then Jn into beta 2. Right? So yeah, you can take few more seconds to note this down. Right? So if you have, see, I'm not going to explain this because it is straightforward. If you go back and see the equation, and in that equation put m equal to 0, just put m equal to 0, then you have J naught of beta 1, and vary n from minus infinity to plus infinity. That gives you Jn of beta 2. And yeah, so what I'm trying to say is, here instead of n is equal to 0, put m equal to 0, and then so that makes this equal to J naught of beta 1. So this makes Jn of beta 2, and this becomes NF2, and this also becomes NF2. Right? Anyway, don't get confused. You can do this. You can do this. No need to copy from the notes. Okay? Yeah. So and then fourth, cross modulation terms. Cross modulation terms at frequencies Fc plus or minus MF1 plus or minus NF2 for m is equal to 1, 2, 3 and so on, and n is equal to 1, 2, 3 and so on, with amplitude. What is the amplitude now? Jm of beta 1 and Jn of beta 2. Right? So yeah. So when we do it, so I hope you have noted down. Then let me go back here. So let me erase this one. So now when I said cross modulation terms, that is equivalent to both n and f, and n and m are non-zero. So what we were doing is, we have kept, so now m is non-zero, and n is also non-zero, and you have delta of f minus fc plus or minus mf1 plus or minus mf2. Right? So that is that The last point is clear from this. Okay. So and now just compare this with FM. Sorry, we are considering FM. Just compare this with AM. So in AM, so in amplitude modulation, when m of t contains when m of t contains two frequencies, contains f1 and f2, then what will be your carrier frequencies? Fc plus or minus f1 and Fc plus or minus f2, right? Say just for example, think about this. So in AM you have 0 and you have this as the carrier frequency. Then you have Fc plus f1. So this will be your Fc plus f1 and this will be your Fc minus f1, and similarly on the left hand side minus Fc plus f1, and here on this side you have minus Fc minus f1. So this is all for f1, and similarly for f2 it will be Fc plus f2. So you will have another component Fc plus f2, and similarly here you will have Fc minus f2, right? Similarly here you will have minus Fc plus f2, here minus Fc minus f2, right? So you have, it's very clear in AM that you will have for two. So there are two side frequencies for for f1. There are two side frequencies for f negative side, and there are other two side frequencies on the positive side for f2. So this is for f2. Whereas here you have side frequencies, you have almost equivalent to infinite number of side frequencies, because Fc plus or minus mf1, m varies from 1 to infinity, n varies from 1 to infinity, right? So this is just comparing with AM. So if you want to compare, as I said, it's better if you can compare it with AM, because you will get to know the differences, right? So this completes our multi-tone FM. So we discussed the frequency spectrum, or the frequency content of a single tone FM with narrowband FM. Like, okay, what we did single tone FM with beta small and beta large. Beta small we called it as narrowband FM, and beta large we called it as wideband FM. And then we discussed multi-tone FM where beta can be large. Then we go to the next topic, the natural topic, which is the transmission bandwidth of FM. Transmission, BW meaning bandwidth. Bandwidth of FM signal or FM wave. Right. So you can understand that the bandwidth comes naturally after the analysis of the FM signal. Why? We have seen that there are infinite side frequencies, right? Even if you execute, okay, here we consider modulation by a sinusoidal signal. Sorry, I'm writing all wrong. modulation that meaning I'm talking about tone modulation. So a sinusoidal signal is also called a tone, right? Yeah. Yeah. So if I modulate with FM, if I modulate with a frequency FM, what we are getting? We are getting infinite frequencies corresponding to FM, 2 FM. These are the side frequencies, 3 FM, okay, sorry, 3 FM and so on. So this is all on the positive side of the spectrum. These are the positive side of the spectrum, right? So strictly speaking, it is what we are having: FC plus or minus FM, FC plus or minus 2 FM, FC plus or minus 3 FM, and so on. So there is a side frequency at FM minus FM, plus 2 FM minus 2 FM, plus 3 FM minus 2 minus 3 FM, and so on. So that meaning theoretically we need infinite bandwidth to transmit an FM signal. Agree? See, you are, even though if you are modulating with one frequency, your FM signal is having infinite number of frequencies. So that meaning you need to have infinite bandwidth to transmit an FM signal, right? So first make a note of it. So FM wave contains FM wave contains infinite side frequencies, infinite number of side frequencies, which implies that bandwidth required to transmit an FM wave is infinity, or infinite is infinite, right? So what is the solution to this? We cannot have infinite bandwidth for us to transmit, right? So the solution is, though it has got frequencies extending from minus infinity to plus infinity, we can choose to restrict the spectrum. We can choose to restrict only a set of frequencies in that infinite frequencies, which contribute to 98% or 99% or 90% of the total power, right? So see, for example, the all the frequencies, each frequency component contains some amount of power, and if we gather those frequency components which contribute to 98% of total power of the FM wave, then that means, okay, we are losing 2% of the information or 2% of the power, but still that 2% may not result in a big amount of distortion, right? So that is the engineering solution to this problem. So a significant, the observation is, a significant amount of total power is confined to a finite bandwidth. We'll see what it is with an example. So a significant amount of total power is confined to a finite bandwidth. So what do I mean by that? Say the total power in FM signal P is equal to half into AC square, right? N is equal to minus infinity to plus infinity Jn square of beta. So this is what we derived in the last class, right? So we have frequency, we have components derived previously. So check your notes. Just in the last class we derived this, right? So just for example, consider let AC equal to 1 and beta equal to 1. So I'm just making the carrier amplitude AC to be equal to 1. And then consider the modulation index beta to be equal to 1. Then if you know these Bessel coefficients, see Jn of beta is nth order Bessel coefficient of the first kind with argument beta, right? So if you see, so if you consider this, then total then and compute, let AC equal to 1, beta equal to 1, and then compute power contributed by n is equal to 0, n is equal to plus or minus 1, and n is equal to plus or minus 2, right? So that power is equal to half into J naught square of 1 plus, I will write it here, 2 into J1 square of 1, because there will be J minus 1 square and J plus 1 square, right? The magnitude of J minus 1 and J plus 1 are same, plus 2 into J2 square of 1. So this is the power if I consider only n is equal to 0, 1 and 2. Okay, and n is equal to 0 and n is equal to plus 1, n is equal to plus 2, n is equal to minus 1, n is equal to minus 2, right? So understood. And we are considering beta equal to 1, and then this power will be whatever this will be. So what I am computing, half into J0 square of 1 plus 2 into J1 square of 1. See why this 2 comes here? Because of J minus 1. We also have J minus 1 plus 2 into J2 square of 1. So this is equivalent to 1 half. So this Bessel function tables are available in textbooks. Say for example, I am taking this example. From Taub and Schilling. In Taub and Schilling, you find this example in Taub and Schilling book, or you can generate it using MATLAB as well. So this is point. Okay, so okay, let me write this. Point 289 plus 0.193 plus 0.013. So that is equal to 0.495. So this is the power contributed by the side frequencies Fc plus or minus F1, Fm I call it because M is the modulating frequency, and Fc plus or minus 2Fm. And what is the total power in an FM signal? Total power in FM signal with AC equal to 1 is half AC square, that is equal to 0.5, right? So 0.495 is how much? 99%, 99% of 0.5. So what does that mean? So if we consider only the first two side frequencies, then we will be losing only 1% of the power, right? So instead of transmitting the infinite bandwidth, if we transmit only bandwidth up to two side frequencies, that means we are transmitting 99% of the FM signal, 99% of the power contained in the FM signal, and the distortion by losing that 1% of power is negligible. Obviously you will have some distortion, right? So you have a total signal, but you are not transmitting the entire signal, but you are transmitting only 99% of the power. See, this 99% is not the bandwidth, it is the power, right? So don't get confused in that. So you are not transmitting 99% of the total bandwidth, you are transmitting, you are computing your bandwidth that is required to transmit 99% of the total power. So to transmit 99% of the total power, you need to consider bandwidth up to only two side frequencies, which is much smaller compared to an infinite bandwidth, right? And it was shown through experimentation. It was shown experimentally that experimentally that if we transmit if we transmit 98% of the power, 98% of the total power, then the resulting distortion is tolerable. Then the resulting distortion means we can transmit only 98% of the total power, which corresponds to only a finite bandwidth of the FM signal. And even if we lose the 2% of the power, the received signal is still good enough for us, is still high quality. So we won't find out any distortion in the received signal, right? So always you find the bandwidth that contains 98% of the total power, right? So hope you have made a note of it, and then I'll move on, like. So if we use bandwidth that contains 98% of the total power, then we can use FM system. Yeah, this is FM system without noticeable distortion. Right, and then it was found out that always for a given value of beta, greater than or equal to 1, we need how many? N is equal to beta plus 1 to have 98% of the power. That meaning, see, this is half AC square, right? This is the total power. N is equal to minus infinity to plus infinity, Jn square of beta, right? This is the total power. So in this, if I consider N is equal to beta plus 1, right? So if I consider only half AC square into J naught of beta plus 2 into so on up to N plus 1 here it should be 2 again, 2 into J n plus 1 of beta. So this gives me 98% of the power. So I need to consider n plus 1 side frequencies on the positive side and n plus 1 side frequencies on the negative side, right? So my total bandwidth, I can restrict that to be 2 into beta plus 1 into FM, right? See this is it was shown by computing the Bessel coefficients that if I consider n is equal to 0 and n is equal to plus or minus 1, so n is equal to 0, n is equal to plus or minus 1, n is equal to plus or minus 2, and so on up to n is equal to plus or minus beta plus 1. If I consider up to n is equal to plus or minus beta plus 1, that will give me 98% of the total FM power. So if I consider side frequencies up to beta plus 1 on one side or side frequencies of 2 into beta plus 1, then that will give me 98% of the power. So my bandwidth required, so and I'm saying that we need to transmit only 98% of the power. So the total bandwidth, we can write that as bandwidth is equal to 2 into beta plus 1 into FM. So because we are considering the modulating frequency as FM. Beta is equal to delta F by FM, right? So beta is equal to delta F by FM. If you substitute that beta here, then this is equal to 2 into delta F by FM plus 1 into FM. So this is equivalent to 2 into delta F plus FM. So the bandwidth is equal to 2 into delta F plus FM. So this is called Carson's rule. Right? So the bandwidth of FM is 2 into the maximum frequency deviation plus the modulating frequency, twice the sum of maximum frequency deviation plus the modulating frequency. That gives you the bandwidth. And note that this is this we derived assuming beta is greater than or equal to 1, right? So the bandwidth required for FM transmission when m of t is a sinusoid with frequency FM is bandwidth is equal to 2 into beta plus 1 into FM, which is equal to 2 into delta F plus FM, and this is called Carson's rule. So when beta is much less than 1, what happens to the bandwidth? Bandwidth becomes 2 into, see this beta is much less than 1. This beta is much less than 1 plus 1 into FM. So when beta is much less than 1, you neglect this. So this becomes approximately equivalent to 2FM. Right? So that completes our bandwidth requirement of FM signal. What we did was we analyzed FM signal, we defined what is an FM, what is a PM, what is angle modulation, and then we analyzed single tone FM, narrow band, in single tone again wide band. So we did all these things and then we found out its bandwidth. Now we want to know how to generate FM signals, like practically how can we generate FM signals, right? So in this there are two methods. One is indirect method. This is also called Armstrong method, because Armstrong is the one who proposed this way of generating FM signals. So I guess, yeah, Armstrong's method. So in this indirect method, first a narrow band FM is generated, and then to increase its frequency deviation, which is beta, we use frequency multipliers, right? See, we have already discussed generating narrow band FM, right? So if you go back and see your notes, you will see that. So when I say now the generation of FM, what do I mean is we want to discuss generation of wideband FM or generation of FM for any arbitrary value of beta, because beta is the modulation index, and narrowband FM is when beta is very small compared to 1. So we discussed how to generate that particular FM. Now we want to know how to generate a wideband FM. So in wideband FM, you know that modulation index is high or the frequency deviation is high. See, what is the physical meaning of narrowband FM and wideband FM? Don't think that narrowband FM beta is less than 1. Yeah, yes, you have to think that narrowband FM beta is less than 1 and wideband FM beta is greater than 1. But what does it mean physically? What does it mean from the signal point of view, right? So in a narrowband FM, the carrier frequency is there, and compared to carrier frequency, the frequency deviation is small. In wideband FM, the frequency deviation from the carrier frequency is very high. Say if the carrier frequency, the frequency deviation can be as high as 75 kilohertz, right? If the carrier frequency is 100 megahertz, and the frequency deviation can be 75 kilohertz in wideband FM, whereas in narrowband FM it can be as low as 1 kilohertz or 2 kilohertz or 3 kilohertz, whatever. So the frequency deviation, the amount by which the frequency deviates from the carrier frequency is small in narrowband FM, and the amount by which the frequency deviates from the carrier frequency is high in wideband FM. So right now we are thinking of generating particularly the wideband FM. Right? Yeah. So in this indirect method, what so this I'll keep it in brackets because we already did this. So in indirect method, we first generate narrowband FM because we already know how to generate that. We first generate narrowband FM. And then use frequency multiplier to increase the frequency deviation. So narrowband FM meaning beta is small, and then we use frequency multiplier to make beta large. So that's what I mean, right? So in the block diagram sense, how do we generate this is we use, say this is the baseband signal M of t. This baseband signal we give it to an integrator, and then we use a narrowband phase modulator. So this is the phase modulator, and this has got, so the modulator should be supplied with a carrier signal, right? So that the carrier signal is generated by a crystal controlled oscillator or oscillator, it's simply, but it is crystal controlled in the sense crystal controlled. You can simply also write this as a oscillator, crystal controlled oscillator. Crystal controlled in the sense its frequency is kept stable. Its frequency is controlled by a crystal of very high quality, and so that its frequency doesn't deviate much. And this phase modulator, see, you know from one of our previous discussions that if you take M of t and then integrate that out to generate 0 to t integral 0 to t M of t dt, and then give it to a phase modulator, the output will be a frequency modulator, right? We did this. We did these two diagrams at the beginning of the FM discussion. And this, as I was saying, we will be first generating narrowband FM. So here, what do we get is narrowband FM. To get narrowband FM, this phase modulator is a narrowband phase modulator. What do I mean by narrowband phase modulation? See, in phase modulation, the carrier phase is fixed without modulation. So when there is no modulation, the phase of the carrier is fixed at some value. And when the baseband signal is applied, when the modulation starts, according to the baseband signal m of t, the phase varies. The phase of the carrier signal keeps varying. So that amount of variation, if you keep it low, then we call it a narrowband phase modulator, right? And from the carrier phase is kept low, it is called narrowband phase modulator. And if you give m of t, integrate that out, and then give that as the input to the narrowband phase modulator, you will get narrowband frequency modulator output. So here we have a narrowband frequency modulated signal with beta small. So this we will give it to frequency multiplier. Frequency multiplier, so that output is wideband FM. Right? So this is called Armstrong's method, or the indirect method of generation. So we'll discuss this in more detail now. So if you have noted this, then let's start analyzing this circuit, this block diagram. See, this crystal controlled oscillator is nothing but to give a stable carrier signal. So this is the carrier signal. So you can write this as AC cos 2 pi FCT, right? Okay. So this integral signal is 0 to t m of t dt, right? Yep. So I'll move on to discuss this. So at the output of the narrowband phase modulator, narrowband frequency modulated signal, and that is given by AC cos. Okay, so we should call it as A1 cos 2 pi F1 t. So let me write this down. So this is, I'm sorry about this mistake. So it is not AC cos 2 pi FCT. You will understand why it is not the carrier signal. It is A1 cos 2 pi F1t. So it is a frequency at F1. It is not the desired carrier frequency. So here at the output you will get FC. The carrier frequency will be FC, but here it is only F1, because this frequency multiplier will increase this carrier frequency as well. The frequency multiplier will increase this from F1 to FC, right? So the oscillator is generating signal at A1 cos 2 pi F1t. So A1 cos 2 pi F1t plus 2 pi kf 0 to t m of t dt. Because see, to the phase modulator you have given input as integral 0 to t m of t dt, and the phase modulator will exactly do this. So this is the output of the narrowband phase modulator, right? And so just for example, when m of t is am cos 2 pi fmt, am cos 2 pi fmt. So this signal will become what? A1 cos 2 pi f1t plus 2 pi kf into integral of am cos 2 pi fmt. So becomes am sin 2 pi fmt divided by 2 pi fm. So this gets cancelled. So this becomes a1 cos 2 pi f1t plus cos 2 pi f1t plus kf into am divided by fm sin 2 pi fmt, right? So this we call this as beta 1. This is the frequency deviation at the output of the narrowband phase modulator, right? So finally what do we have? A1 cos 2 pi f1t plus beta 1 into sin 2 pi fmt. So let me erase this one. So beta 1 is equal to kf into am divided by fm, right? Now the output of the fm, the output, this output is given to the frequency multiplier, right? See here. So here we have this narrowband fm. So whatever equation we have written in the next page is the output at the narrowband phase modulator. So which is equivalent to the narrowband FM modulated signal. That signal is being given to a frequency multiplier. So this frequency multiplier, what it does, let us see. So this is being given to a frequency multiplier. So this signal is given to frequency multiplier that multiplies the frequency by n times. So let's assume that multiplies the frequency of the input signal by n times, right? So if we multiply the frequency of the input signal by n times, what do we get? Here we get n, and here also we get n. So the output will be, oops. So we have again run out of pages. So I'll delete one of the previous page, and then yeah, we have this input to the frequency multiplier cos 2 pi f1t 2 pi kf 0 integral 0 to t m of t dt. Now it is being multiplied by a frequency multiplier having a multiplication factor of n. So you get this, and then again consider when m of t is equal to am cos 2 pi fmt. We get the output of the frequency multiplier as so this okay, so see, strictly speaking, the frequency multiplier doesn't change the voltage, doesn't change the amplitude, so maybe I should still write this as A1 cos 2 pi fct plus beta sine 2 pi fmt, where fc is n f1, because the input is f1, that is being multiplied by n. So the new frequency nf1, I am calling it as fc, right? And beta is equal to n beta 1. See, the input to the frequency multiplier has got it's a narrowband FM signal with frequency deviation beta 1, right? And then the frequency deviation is also getting multiplied by n. So the new frequency deviation beta at the output of the frequency multiplier is n beta 1, right? So n beta 1 is n into delta f by fm, right? So that is equivalent to n kf am divided by fm. Okay. So see, I simply said a frequency multiplier multiplies the frequency by n units or whatever. So let's see one example of a frequency multiplier. So frequency multiplier, so this will help you to understand what is this frequency multiplier. An example of a frequency multiplier is simply a square law device will multiply the frequency by 2. So a square law device, consider a square law device. So what do I mean by square law device? In a square law device, output V0 of t is equal to square of the input, right? So the output V0 of t is nothing but square of the input. So that is a square law device. So you know, if y is equal to x square, if x is the input and if the output y is equal to x square, then that is called a square law device, right? So let's assume we have a square law device, and a square law device, it achieves frequency multiplication by 2. Right? So let's assume the input to the square law device is narrowband FM signal. Sorry. Okay, I have to delete this as well. So let Vi of t is, I'm simply writing AC cos, okay, this a cos 2 pi f1t plus two pi kf 0 to t m of t dt. Then what is its output? Output is equal to Vi square of t. So that is a square cos square 2 pi f1t plus 2 pi kf integral 0 to t m of t dt. So this I can write this as half into, so this is half 1 plus cos 2 theta, right? Cos square theta is half into 1 plus cos 2 theta. So 2 pi 2 f1 2 pi into 2 f1t plus 2 pi into 2 kf into 0 to t m of t dt, right? So what happened? The carrier frequency increased from f1 to 2f1, right? See the carrier frequency, and we will use a band pass filter. See, we have a DC term as well. We will filter this DC term. So the carrier frequency has increased from f1 to 2f1. The kf has increased kf is sensitivity of the modulator, right? So the kf is sensitivity of the modulator, and we know that modulation index beta is equal to delta f by fm, and delta f is what? Kf into am divided by fm, and now this kf has increased from kf to 2 kf. Understood? See, previously in this signal we have some beta. That beta is equal to kf into am by fm. But now after see in this we have beta. Beta is equal to kf into am by fm. But after giving this to a square law device, and the square law device output is this, so the kf has become 2 kf, so your beta has become 2 beta, right? So the kf has increased to 2 kf, increasing beta to 2 beta, because previously beta is kf am by fm, that is some value. Now the kf has become 2 kf, so beta has become 2 beta. So that means the carrier frequency has become doubled, and the frequency deviation, or the modulation index beta, modulation index beta, that's how a frequency multiplier works. So if you give input to the frequency multiplier, if you give a narrowband FM signal, the carrier frequency also will get increased by n times. So don't think that only the frequency deviation will get increased by n times. No, it's also the carrier frequency. The carrier frequency will also get increased by n times, right? So that's why uh, yep. So that's why in that block diagram, the first crystal oscillator is operating at frequency f1, and it produces a narrowband FM signal with frequency deviation beta 1, and then when this signal is given to the frequency multiplier by n times, the carrier frequency gets increased from f1 to nf1, right? So from f1 to nf1, uh, for this, yeah. So the frequency, the carrier frequency gets, frequency deviation also gets increased from beta 1 to n beta 1, right? So that's how the indirect method works. and then what remains is direct method. So I'll just quickly introduce in 2 minutes what is another method of generating FM is direct method. In direct method, the frequency signal is varied directly in accordance with the baseband signal m of t. And we vary this using voltage controlled oscillator. Voltage controlled oscillator. So that meaning that oscillator's output frequency is controlled by the voltage applied to it, and if the baseband signal m of t is a voltage signal, so whatever the audio signal or speech signal is we give it as a voltage signal to a voltage controlled oscillator, then the output will get modulated. So how this is done in general is something like this. So it is based on say LC circuit. So I'll take 2 more minutes and then I stop. Yeah, I know that you may be having a next class. So it is something like this. So there is L, and there is a fixed capacitance C naught. So this is a fixed capacitance C naught, and there is a voltage variable capacitance CV. Say this CV varies according to the voltage applied to it. So this is m of t. Right. So we know that the frequency of any resonant circuit is given by 1 by 2 pi root LC. Right. But here C has two components. One is fixed value C naught. Another is CV varies according to the voltage signal. M of t. So when m of t varies, CV varies, right? This capacitance varies, and when this capacitance varies, the effective capacitance varies, and when the effective capacitance varies, this frequency of the output varies, right? So there is a particular way of generating this, which is called Hartley oscillator. So we'll discuss next time. Yeah, Hartley oscillator. So anyway, so in generating wideband FM, there are two methods. One is indirect method, which is also called Armstrong method. So that we discussed, and then the direct method I haven't completed, but I just gave you the idea how it is done. It is based on voltage controlled oscillator, right? So yeah, with that the time is also up, 10:40. So let's stop for today. And Asghar, is this the last class before Pongal?